talk about conformal bootstrap or boundary link, boundary Liouville CFT.
So not really, but I will talk about boundary Liouville CFT, but not about the conformal bootstrap. I think it's Baojo. So I think what I would be interested in is to study boundary Liouville CFT. But what I would like to do is to study both like the classical theory first, and then the theory which is a bit less classical. I would call it random, not to put quantum because it's always and, yeah. So first of all, thanks to the organizers for giving me the opportunity to speak here. It's always a pleasure to be Diableret. First time in summer. I appreciate it. So this talk will be like I won't give out a lot of big results. I won't hammer you with complicated things. I will try to stay at a high level. Nonetheless, I will try to go back commercially. I will try to go back to the basic questions related to Liouville CFT, which is to try to understand what brought us in the first place to study this kind of theory, and why we even consider this kind of this Liouville action functional that Rémi talked about yesterday. So without further ado, let me fix a bit the context. So I will take sigma j to be a Riemannian surface, which I will assume to be compact, or like connected, oriented, whatever. And we assume that it has a boundary. The boundary, as usual, it will be denoted. Something else that I would like to set for the rest of the talk is something like so I would like to introduce some numbers, some weights A and some points ZK. So familiar with them. So I do this, I think many people call this a divisor. Okay. So I introduce a divisor where the weights AK and BM are assumed to be strictly greater than -1. So it corresponds to one side of the cyber bond. And ZK is a point in the ZK are points, punctures on the surface. And it's SL that belong to the boundary on the surface. Okay, so we will keep this protagonist for the rest of the talk. So what I will try to study during this talk is so I'll basically be interested in two related notions, like classical Liouville CFT and its random analog. So what is the classical boundary Liouville CFT? So basically we're interested in the following question. So the classical question inherent to Liouville CFT is the following. So it asks for finding a conformal metric, D prime, which takes the form e to the phi j, which is smooth or regular enough outside of the punctures, so the support of my divisor. Okay, this is one thing, but near these singular points, what I would like is the following. I want it to have conical singularities. At all these singular points. And the angle of the singularity is prescribed in terms of this A and B. So the angle would be theta k equal to 2 pi 1 plus AK. On corners, at all these boundary points, and the angle this time is parameterized as pi 1 plus BL. So this is one assumption that I want my matrix to satisfy.
AK is defined up to an integer.
To n
if you add 1 to A, the angle doesn't change.
Well, wrap around. So if actually there will be a change. There will be a big difference. Like 2 pi is not 4 pi. We come to that later. Yeah, so you want conical singularities. Then what you also want is something related to uniformization. Is you want it to have constant, not constant actually, but you want that it's Ricci scalar curvature. So I use the Ricci scalar curvature, but it's the same as up to factor 2. As the Gaussian curvature. So I want its scalar curvature in the bulk to be given by minus lambda. And I want also to prescribe its geodesic curvature on the boundary to be given by minus sigma, where what are lambda and sigma? I assume this to be positive. So lambda and sigma are both positive, non-negative, sorry. And I will assume that lambda is not always 0, otherwise it's interesting. And I assume that lambda is, say, smooth. Lambda and sigma are smooth away from the support of the divisor, from all the singularities. So the question is a bit the following. So imagine that I have a sphere, like I cut it in half. So I have like a disk, which is not flat. And I pinch it at several points. And I want to find a metric which realizes at this kind of uniformization, but we have a tiny subtlety. And the subtlety, what is it? Is that this sigma, typically it will not be constant. So this lambda, typically it will be chosen to be constant in agreement with the uniformization problem, but this sigma, it can be piecewise constant actually. So for instance, if I take the example of the disk, so I can pinch it at, on the boundary at 3 points, I can also add a bulk singularity on this. So this is a disk finished here on this boundary. And typically, I will ask for like constant negative curvature inside, but on the boundary, I can ask for like the geodesic curvature to take 3 different values: sigma 1, sigma 2, sigma 3. Okay, so maybe. So this is
already revealed why you want to do this, or?
So I can do that either now or a bit later. As you, I can explain the relevance of this, but maybe I would like to do it a bit later. Actually, so the following. So you want to find like it's related to uniformization of Riemann surfaces. Like if you want to find a complete algebraic metric on your surface that is. Case, you assume this to be like 1 constant, and you want the boundary to be geodesic. Yeah, it is just information. Yeah, I will come back to that later. Yeah. So this is the classical problem that we will be interested in. And in the Liouville CFT, what you do is, so you start from this kind of classical deterministic geometry, and then starting from this, you build a random geometry, a notion of random geometry. So in Liouville CFT, what you do, you define a random geometry, a notion of random surface, with shape fluctuates in some whatever fluctuates around this classical geometry. And of course, if you want to go from 1 to 2 what do? So you formulate it in terms of a variational problem, you make it into a path integral, and you end up with this Liouville CFT, which is indexed by some randomness, like coupling constant gamma, which is some kind of which is a coupling constant which gives you a level of randomness of your model. So it can be thought of as a square root of h bar, if this is correct scaling. And the nice thing is, on this side, you have a lot of tools. On the side of Liouville CFT, you have plenty of techniques. Like you have these Ward identities, OPEs, and you have DPZ type differential equation, which in our case will be actually a equation of motion. And then, what you would like to do is to bring back some CFT machinery from this, the world of CFT, to the classical setting, and to see what it tells you about your model. Look at it, your first question. So doing that is called semi-classical limit, and I think we maybe hear a lot of this. I think we already heard, and we surely hear about this in other talks. So basically, the plan of the talk today is just to first discuss this classical problem, then move to the CFT and explain to you how these two relate together by explaining how to take this semi-classical limit. And then, if we have time, yeah, we'll see some classical implications, like what CFT techniques can tell you about this very classical problem. Okay, so far so good? Any questions? Okay, so the first part is this classical problem of prescribing curvature and conical singularities. So first of all, the first thing that you may want to do if you want to solve such a problem is to translate it into some language with which you can do some things. So first of all, I need to say what I mean by conical singularities on corner. So basically, saying that G has a conical singularity or a corner, it's the same, at zk with this precise angle, the theta k that I wrote before. So what does it mean? It means that the G prime, sorry, that means that the conformal factor, so recall that G prime is exponential phi j, G, phi G. If the conformal factor in the neighborhood of zk, it behaves like minus 2 ak logarithm of the geodesic distance between z and zk plus the big O of 1. So this is my definition of conical singularities. And basically, if you are not convinced, well, actually it's yeah, you can play with this definition and see that it's a very good one. So this means that if I want to, first observation is that if I want to solve this problem, therefore, I can first take out all these singularities from the field, and I can write that phi is on the form, so a var phi plus some hza, so as a density to my divisor, where what is the hza? The h will take all the singularities. So maybe I can take another pen.
When you write over 1, what is becoming smaller? Or
Sorry?
when you write over 1, what is the limit?
It's z goes to zk. So near a singular point, your metric is locally. No, I mean, yeah, the conformal factor behind like this. So the metric is. Which is near a puncture. And the way to achieve that is you can desingularize your problem by putting all this singularity into this function that I call hza, which is nothing but sum from k equal 1 to n of minus 2 ak think there is. It's a plus. Minus 2 G D ZK minus some BL where G, what is G? G is green kernel, so it's a Neumann green kernel. Neumann Green's function. And the reason why it satisfies this property is that if you take this Green function and you take a point in the bulk, so you know that it has singularities on the diagonal. That is when Z goes to ZK, the Green function will have this behavior.
You fix a metric first.
Yeah, the metric is fixed. So here the metric is really fixed. So I have chosen the metric G. Yeah. So here I won't touch this. This is fixed for yeah. So yes,
You consider the only metric in this conformal class.
Yeah, exactly. Yeah. But this metric is generic, and G is generic. It can be anything as long as it's smooth. Yeah. And so you can find a Neumann Green function. On the nearest bulk point, it has a singular behavior. Like I mean, without the 2AK, it's below. And also boundary points, the Neumann Green function behaves like 2 log. So this is why here you have BL instead of this 2AK. Here, so I've made this decomposition where H takes all the singularities, and my phi now is continuous or smooth or whatever. Okay, we say smooth. No, okay. I have this as follows. Now I want to transform it into something which I can really solve. So what does it mean to that for this metric G prime to have this this curvature on the geodesic curvature given by minus lambda on minus sigma. So basically there is a famous rule for the change if you make a change of a conformal metric, a conformal change of matrix, in dimension 2. That in my new metric G prime, which is exponential phi j, the Ricci scalar curvature transforms as exponential minus phi times the initial curvature, Rg, minus the Laplacian. My Laplacian is negative, so minus Laplacian is positive. And we have a similar rule for the geodesic curvature, which is we transform as exponential minus phi over 2 times the initial geodesic curvature plus 1/2 of, so you take the normal derivative of phi. And so, if you take this, you plug it into this equation, you see that what you want to solve is the following PDE. So you want to solve the equation Laplacian phi, so this Laplacian depends on the metric. At some point I will just drop the G. Is equal to Fj plus lambda exponential phi plus h and sigma. On the boundary, you want to have minus 1/2 normal derivative of phi is equal to kj plus sigma plus h. So you have the PDE, and you can ask whether it has a solution or not. Good. Seems like everyone is sleeping. So So this is something that you want to do now. Question is, how do you solve such a PE? So first of all, you may want to find some necessary conditions for the solution to this problem to exist. And there is an obvious requirement for a solution to this to exist, which is given by the Gauss-Bonnet theorem, Gauss-Bonnet formula. So what is the Gauss-Bonnet formula? So here I have the thing, I have a singular metric, so I will need to be a bit careful. So the first obstruction is the Gauss-Bonnet formula. So if I integrate the curvature plus this kg over the whole surface, I have a topological impact. So the Gauss-Bonnet formula, what is it? It's I integrate the Ricci scalar curvature with respect to the volume form given by the metric G on sigma. I integrate on delta sigma the geodesic curvature with respect to the line elements. And I need to put some constant, 1 over 4 pi, 1 over 2 pi. The constant 2, it's because I taken Ricci scalar curvature instead of Gaussian curvature. And usually, if I have a smooth Riemannian metric on my surface, this is a topological invariant, which is the Euler characteristic of the surface. The thing is, in my case, the metric will be singular. It has conical singularities. I'm breaking all the chunk. So if I change G to G prime, which has conical singularities, I will need to add some extra term, which is given by sum of the detail plus 1 half sum of the detail. And this I will call singular Euler characteristic. And you see that if you do that on this expression, what you will get, like in the thing that I raised, the necessary condition for the existence of a solution to my initial problem is that this Euler characteristic is negative. So the necessary condition for the existence of a solution is that the Euler characteristic is negative. And actually, the claim is a sufficient one. So the theorem, so my initial problem, so my problem 1 has a unique solution if and only if the Euler characteristic is negative. Okay, so now we can do a bit of history. So why is this problem interesting in the first place? So actually, I think this problem, the problem of finding a solution to this Liouville equation. So if you take this, not the simplest, but like the canonical example, which is you take flat reference metric, you take this lambda to be constant given by -1, and you don't put a boundary, or you put some like boundary conditions, inaccurate boundary condition. This is a problem that was asked a long time ago. I think from the Royal Society of Computing anyway. And that was answered by Picard in 1890. So I think the first answer to this problem is due to Picard. And the first answer came in 1890. And there is actually a series of papers by Picard, because apparently in the first place he made a generalization a bit too fast. But actually in the subsequent papers, without conical singularities, sorry. But actually in the subsequent papers, Picard also addressed the case of conical singularities, which is, I think, quite amazing, quite remarkable. Next, in the story, you have another big name, like Poincaré. what actually got interested in this problem because it was a way for him to prove uniformization, uniformization of Riemann surfaces. Basically, he was interested in solving. So in this 1898 paper, and the equation Fuchsian, blah blah blah. He was interested in uniformization of a puncture sphere, and in that case, so it turns out that if you want to uniformize the puncture sphere, you may want to solve the Liouville equation, which is sometimes given by 1. And the conical singularities are actually not, as I put, the weight is actually -1, equal to -1, but then you need to add some corrective term. So I don't remember so the name of the singularities in modern language. Either it's parabolic or elliptic. Parabolic, I think, yeah, elliptic. So sommet de la troisième espèce.
But what was his motivation to have that?
Uniformization. Like if you want to uniformize a puncture sphere,
You have the horocycle.
Hmm?
He put the horocycle around the...
Yeah. So basically you can write, I think it's developing map or whatever. You can express it in terms of solution of a Fuchsian equation. So this equation that goes back to Poincaré, like a long time ago. But in that case, so this lambda was chosen to be always a constant. Like typically 1. Then actually, so this is more related to uniformization of Riemann surfaces. Like a more recent problem is called the Nirenberg problem. So this is like uniformization. The Nirenberg problem asks another question, which is like, under which conditions is a function the curvature of some smooth Riemannian metric on a surface? And actually, so this is a question that was answered first by Berger in 1971, where he provided necessary condition, sufficient condition for a function to be the curvature of a Riemannian metric. So basically, the answer by Berger was if you take lambda, which is satisfying our equation, today's equation, like so today's assumptions, like it's strictly positive, then it's the curvature of some metric. And the way Berger proves this is using a variational approach. And a definitive answer that was then provided by Kajdan Warner a few years after, so I think it's 1974 or 3, yeah, where the Nirenberg problem was solved for a closed surface. And basically the condition that the Euler characteristic, like the integral is negative, and that the K must change sign once, at least once. So this is a bit like the historical picture. So this was like on the case without boundary, and maybe here without conical singularities. There is also a story in the boundary case, like something done recently by Lopez, Soriano, Malchiodi, and Ruiz from 2018. In the case that we are interested in, the case of conical singularities, actually, this you have a famous paper of Troyanov from 1991, from his PhD, I think, his PhD, where basically he proved our statement in the case where the geodesic curvature is the curvature is geodesic, so it's 0. So this problem 1 has a long history. I hope that now you're convinced that it's interesting. If not, you can have a look at boundary Liouville CFT and see all its amazing developments, and then I guess you'll be more than convinced. So then, how do you solve, what kind of approach do you use to solve this problem? So I think Picard and Poincaré used some different methods which are rather different than the ones that we use today. But actually, Poincaré in his essay already introduces the Liouville action. So basically, you can formulate this problem variational formulation, which is that you consider functional over some functional space, and you want to find its minimizer. And actually, the variational formulation is made in terms of what we call now the Liouville action. And that was actually, so if you look in Poincaré's essay, chapter 9, you can find the Liouville action. This is not what he uses actually to prove his statement, but he gives a physical motivation using this. Which is quite amazing, I think. So what is this Liouville action? Liouville action, so something that takes as an entry a phi as before, which I decompose as var phi plus h, and which is defined, at least heuristically, as follows. So I have a first term which is square gradient. All of this depends on the metric. Then I have 2 rg phi plus 2 lambda exponential phi in the metric g plus 1 over pi g phi plus 2 sigma exponential 1 phi ELG minus this is so the Liouville action is formally defined as follows. However, the thing that you already see from this this decomposition that you cannot evaluate h at the singular points. In particular, this does not make any sense. But what you can do is to work with a regularization. So instead of working with phi, you regularize it. So you change phi into phi rho, which is average of phi on geodesic circles, or semicircles if you're on the boundary, anyway. So you change phi to phi rho. And then you see that this action, you can see explicitly how it diverges as the rho goes to 0. And basically, the way it diverges, you have a singular term which is proportional to the logarithm of rho. And so, if you subtract this divergent term, you get something which is well defined in the limit. And so, this is how you define the Liouville action. And actually, if you decompose phi in terms of var phi plus h, what you get is a functional that I will denote with a I don't know why, but anyway. You get a functional I which takes as an entry some smooth function at first. But actually, this IZI, its functional, is well defined. Over the Sobolev space. So this is the well Poincaré these tools, these modern tools. So it's well defined over the Sobolev space of the index 1. And why is it well defined over H1? So this first term is of course like okay for H1, but then you need to make sense of the exponential of an element of H1. And to make sense of this, you use something which is called Moser-Trödinger inequality. So Trödinger came up with inequality, and Trödinger gave the optimal constant, I think, this is the story. And the Moser-Trödinger inequality tells you basically that the exponential gives you a compact embedding of the Sobolev space into some LP space, into an LP space. Yeah. Maybe should I write this inequality, or you just you can live survive without it? I think you can survive without it. But it's quite amazing. Actually, it's related to moments of GMC visuals. Anyway. So you have a functional which is well defined over H1.
Sorry, how was the I defined?
It's just you write phi as a phi var phi plus h. You expand, and this gives you a functional over I, of phi. It's just I'm too lazy to write.
Okay.
But typically, you just you forget about this part. You change all this phi to var phi, And here you get var5 plus h.
And you take the limit.
And you take a limit.
Okay.
But you actually don't even need to take a limit. So you have a functional which is well defined about it. Okay. So now you want to find a minimizer. You want to prove that this functional admits a minimum. So after you proceed, then you have all this kind of nice tools from functional analysis. This is like a bit standard now. You prove that it's coercive, which is not too hard to see. So from its expression, you know that I then A is coercive. Thanks to the Moser-Toninger inequality, you know that it's weakly lower semi-continuous. Now, what do? You do a formal expansion. If I perturb phi by a delta phi, a small variation, we do a small variation, what do I get? First order I have, so constant order I have phi. If I look at the first order term in delta phi, what do I get? 1 over 4 pi will be 0, 2 pi, I don't know. So it's delta phi, so 2 pi. Delta phi times minus Laplacian phi plus RG plus lambda exponential phi plus h. Okay, this is at second order, at first order. Now, what is the next term in the expansion? That's third advance plus lambda exponential phi. Exponential delta phi minus 1 minus delta phi plus maybe there is a factor 2 which is I think it's a 2 point. Who cares? And so this explains why I've considered this functional in the first place. Basically, what this equation tells me that if I find a critical point of this action, so this must vanish, so I am a weak solution of my initial problem, and then by some elliptic regularity or whatever you want to call it, I am solution of this equation. The next observation, so this is one observation, critical points describe solution of my initial problem. The second observation is this minimum must be unique. So this is due to the fact that this action is cyclic convex. If you just look at this term, it's quite obvious that the limit is must be unique. So I is strictly convex. Strictly convex. So simply it admits a unique minimizer over H1. Minimizer over H1. And this concludes for the proof. Okay, so now we have solve our classical problem, we can move to quantum world, like at least a random, where the geometry that we define is not deterministic, but iterates around this classical solution. So this is Liouville CFT. So, by the way, how much time do we have? As usual, it will be a disaster.
20 minutes.
Fair. So what is boundary Liouville CFT? So formally speaking, you want to define, the initial point is to define using a path integral a Borel measure. So you want to define a Borel measure. On the functional space that you may first want to be H1, which is defined by taking, defined by associated to any functional, continuous functional phi or H1. Something that will be noted that way. And there you want to weight. So this is so you have the uniform measure on H1, which is of course straightforward. This is a path integral, and you want to weight this uniform measure using the Liouville action. And you want to do that, and you want to introduce a coupling coupling constant, which determines the level of randomness. So what you do is you first multiply this term by 1 over gamma squared, and then you look at the rescale field gamma phi. The thing is, you need to change a bit your action if you do that. There are some anyway. So you need to change the action. So basically, the term 2rg needs to be changed. So what you would get if you do this heuristically, you would have a 2 over gamma rg. You need to change it in 2 gamma plus gamma over 2 rg. And the same for the geodesic boundary. And so this gives you like a path integral definition of Liouville boundary Liouville. Well, of course, if you want to define it properly, a rigorous definition is made using the EPFL. So you see that in your action you have the quadratic term and you integrate over h1. So basically you want to invert the Laplacian over h1. So basically x. So you write it in terms of x, which is a GFF with covariance kernel is given by the inverse of the Laplacian. So formally speaking, it's minus Laplacian over 2 pi minus 1, where this is the Neumann Laplacian. And what it means is that its covariance kernel is the green function, Neumann green function that we talked about before. So this is what Rémi presented, I think, like it's Neumann here. And maybe I'm not going to do the construction of Liouville CFT because it's been already done in a few places. Maybe what I can do now is to try to check the consistency of this definition with the classical problem. That is to say, I will try to see whether this expression is compatible with the gamma goes to 0. Because I think this is one of the most elementary questions that you should ask yourself when you do when you want this kind of path integral is to what extent is it compatible with the classical model that you consider? I think this is the first question that I ask myself.
You could around this blackboard so we see them? Thanks.
And then here you need GMC to make sense of it. I'm not going to interact with it. I'm just going to do some formal computations with the part integral. And of course, yeah, this is supported on H-1 actually. So what happens when gamma goes to 0? What you expect if you do some Laplace method in that this integral will concentrate on the minimum of the action. So a way to do that, to see that, is so you know that I will use this for this video, otherwise I'm lost. So if you do Laplace method, when you integrate, you can make a change of variable. You make a change of variable, phi gives phi plus 1 over gamma in the classical field. So I call this minimum phi star, which is phi star over phi star plus h. You make a change of variable, phi plus 1 over gamma phi star. And here you have 1 over gamma squared s of phi star plus gamma phi. Okay. So at first term, minus gamma squared, the minimum is S of phi star, is the minimum of the Liouville action over H1 functional space. And then you expand it. But the nice thing is I have this explicit expression. I know already that my first term vanishes because I am at a critical point of the action, so my first term vanishes, and I only have the second term. And then what happens if I take delta phi goes to 0, so I expand the exponential, and what I get in the end, it's just formal computation anyway. Exponential minus, you do your DL, Taylor expansion, and then what you get is 1 over 4 pi grad phi squared plus lambda phi squared. Maybe there is 2 minus 1 over 4 pi delta sigma phi squared d phi. And what is this thing? So basically, what you want to do, what you want to say is that the object that you define is a massive Laplacian. So this should be like a massive Laplacian, massive GFF. Massive GFF. But actually, you also have something happening on the boundary. So it's a massive GFF, which has some kind of weird boundary condition. So it's a good friend of Neumann, it's Robin. So the massive GFF with like some kind of Robin boundary condition. So this is what you expect if you do the formal computations on this path integral. And the statement is that this is actually true. And so this is something that was proved by Hubert Lacroix, Rémy, and Vincent Vargas. Like two times, like I think 17 and 21, I think. In the case of a sphere, in the case you consider a sphere and lambda is constant, but actually, yeah. So theorem is something that I will put in the archive as soon as I'm motivated to do it. In that actually this asymptotic is valid. So you can prove that if you define this probabilistically, minus 1 over gamma phi star. So this is defined using probability. Defined using then this actually equal to exponential minus 1 over gamma squared, the minimum of the Liouville action, times something, some f gamma, where f gamma has a good limit, as a limit when gamma goes to 0. And this limit gives you actually a massive GFF as well. So basically you have some Gaussian with some variance v divided by square root 2 pi v, or 2 pi over v, I don't know, but something like this. So you have the constant mode is like a Gaussian. But the field here that you have is a Gaussian free field whose covariance kernel is given by inverting this the operator which are associated to this. Okay. So this is a mathematical statement. Like this is fully rigorous. It's not. So you can actually give a meaning to all these steps that I'm just doing, like doing unwavy computation. But the thing is, so to do this change of variable, what is it in the CFT? So in the probabilistic world, change of variable, it's somehow this Gersonov theorem, like the complete the square. And then the thing which is a bit tricky is that you need to prove some kind of uniform integrability for probabilistic. You need some very deep probabilistic estimates, for which all the credit needs to go to Hubert. And I must say also that something similar, a similar statement has been proved by the Promit, Harini, Andrei Prokhorov, where instead of like correlation function, consider like a probabilistic conformal blocks on the torus, but maybe you're going to talk about this tomorrow. So. Okay, so do you want me to detail the proof or just everyone's already dead? So no. So actually, so what I'm explaining now is that there is a classical theory. You can make sense of the path integral using probability. And using probability, you can go back to this classical setting. And the thing is that I've not gone into details. That on the Liouville CFT side, you have all of these probabilistic, all of these CFT techniques. And you have these Warden entities, DPZ equations, error equation of motions. And actually, this has strong classical implications. Maybe I'm just going to. I promised going to throw some results. But okay, what does it mean to have some classical results based on these techniques? So I will talk first about error equation of motion, which I think is quite nice. It's quite an interesting thing. So what does CFT, in my simple mind, what does the CFT provide us with? So CFT tells you what kind of functionals of the field you want to study. What functional of the field makes sense and gives you some integrability results. So, for instance, there are a few functional of the field that I may want to consider. As the Liouville field. But actually, the story is with the Liouville field. When I say Liouville field, it will be first in the CFT world, when this Liouville field is like random. But actually, you can forget about random and just take the classical Liouville field. That is the solution of our PDE. So here, maybe I assume that sigma is the operator plane, like with the metric G, which is so you just cut sphere in two. So for instance, what kind of functional are we naturally led to considering? Something that I will call L-1. So remind you of something. So I take the boundary insertion, d beta, it's dt, so it's minus, yeah, it's beta over 2 dt phi exponential 1/2. Beta phi. So this is a functional of my Liouville field. Of course, your field is not regular, it's an element of H1, H-1, so you want to give it a proper meaning. But if you give it a proper meaning, what you expect from this, a good definition of this object, so a good definition, you'd expect that when you put it within correlation function, L-1 d beta t, this is just the derivative with respect to t of the correlation function. So this gives you one natural observable of the Liouville field to consider. And actually, if you want to define this, it's a bit tricky. But you can. Another observable I would like to introduce, so you have the second order derivative in the field, which is you differentiate twice the exponential. d2 phi plus beta over 2 dt phi squared. And then you would get a second order derivative. Another one is this L-2, which is sometimes the descendant of this E beta, L-2 descendant. Like you do the OPE of the stress energy tensor, and the constant term is this one. So it's Q plus beta dt over 2 phi minus dt phi squared beta over 2 phi t. If you, what you expect from this is that this gives you word identities. So what you want is this L-2 when you put it within correlation function, this gives you word identities. So sum over k of d k, t minus k, plus delta k, t minus k squared. Okay. I'm going a bit fast because I think I will be late as usual. And you imagine that when you define this object in a good way, it will give you word identities. And then the observation is that if you take beta to have very special values, so if you take for instance beta to be either minus gamma over 2 or minus 2 over gamma, then what you expect, if you do a formal computation, is this the linear combination which vanishes of the L-1, 1 and the L-2. And so the observation is that if you take beta equal either minus gamma over 2, minus 2 over gamma, this is like a stupid computation. This you can find a linear combination that annihilates both. So 1 over beta squared L-1 plus L-2 d beta is equal to 0. But there is, of course, an arnaque. This is actually false. And the reason for that is because we are on the boundary. In the bulk it's true, but on the boundary it's false. And actually, this will give higher equation of motion. So if you take, so in the bulk, this will give you BPG equations. So the statement, the theorem, say if you want. So it was proved by myself last year, but also on a slightly different way, different setting, I would say, by Guillaume and Baojun. And so I give also credit to them. In that, when you insert this within correlation function, actually, 1 over beta squared dt squared plus the scale equality t over t, like this differential operator. You apply to your correlation function. It's not 0, like what you would expect, but it's equal to some function of lambda and sigma. So this depends only on sigma. And here you have V beta plus gamma. V beta plus 2 gamma. So basically what this tells you is that your singular vector, so this is a singular vector, this combination is singular vector, but it's not a null vector. So actually if you think in terms of highest weight modules, this means that your module is not irreducible. It has a proper submodule, which is the image of this singular vector. Which is a nice feature, I think, because usually the modules that you consider are irreducible. And this provides an example where the modules are not irreducible. Now I'm running a bit late, I think. So now you can see what this tells you in the classical world. Is HM, what do they become in the classical world? And actually, what you get is something non-trivial. So you start from you just go like Poincaré or anyone. You take the solution of your problem. With it, you define the stress energy tensor. The thing is, the stress energy tensor is not well defined on the boundary. There is a major subtlety. It's not differentiable actually. Your field has some singularities when you differentiate along the boundary. But still, you can define a stress energy tensor using some kind of regularization procedure. And actually, what you will get is in the bulk, you'll get this. This is the light. So here, I forgot this is a B equal minus gamma over 2. So this light one will give you some equation of motion. There is something which does not vanish, disappear in the limit. And the limit, what you will get. So this T of T will become something explicit, the stress energy tensor, the classical stress energy tensor. But the left-hand side will not vanish, which is quite...
Yeah. So can you make your singular vector vanish by assuming the boundary parameter has an appropriate jump?
Yeah, exactly. So this is the way we do, like people solving a boundary Liouville CFT do it. They assume that these parameters, the boundary parameters, they choose them in such a way that this vanish. Then you have BPG equations, and starting from then you can prove some quite impressive results. In general, if you don't make such an assumption, it's not zero. But you can actually this one is conic. This one is just like a linear combination of this sigma and the two endpoints of yeah. So you can verify. But so on this, in the classical limit doesn't vanish, and you get, so maybe I just finish on that, you get something, so when the gamma goes to zero limit, you get some classical higher equation of motion. So you get some classical equation of motion. And the nice thing is that you have the classical stress energy tensor, and this heuristic approach allows you to compute this stress energy tensor. It's like you know these accessory parameters. Basically, you have the Polyakov made like a prediction concerning these accessory parameters that you can express them in terms of derivative of the Liouville action. And actually, using this probabilistic approach, you can prove a Polyakov prediction in that case. So sorry for being late. It's yeah, thank you.
Questions?
Can you get some logarithms out of this?
Sorry?
Can you get some logarithms out of this?
Some logarithm? Ah.
So like in yet in decomposable or this?
I guess if you want to get a logarithm, what you need to do, so here I've assumed the weight. So at the beginning I made this assumption that a was greater than -1. If you take a equal -1, then you get some kind of it's this derivative. I don't know what this Q vertex operator. But basically, you can make sense of it. You can find the logarithm doing that. If you take this a to be -1, because then you need to add an extra term. But when you say your logarithm, where
Can you find some log parameter to the stress energy tensor?
for the stress, no. I don't know how to do that. You can add some
But
extra
you
looks.
almost said all the ingredients to have such a situation, no?
Well, if
Do
you
you
know
expect this
to
as a classical limit?
I don't know. You have thought about this properly.
I will think about it. Yeah.
So if you take surface with boundary, let's say no puncture,
Yeah.
there is a unique point carré metric, the hyperbolic one, which is complete,
Yeah.
which explodes at the boundary.
Yeah.
Does it fit in this picture or not at all?
So I assume like compactness. So my metric is smooth at the boundary. So that would be interesting. Yeah.
And if you take the partition function or the correlation function,
Yeah.
let's say you put the hyperbolic metric as a background metric. Like now, the Liouville correlation function, and you make a variation of the background metric.
Yeah.
This produces a cotangent space to Teichmüller.
Mm.
It's a analytic differential. So this corresponds to a projective structure because you can compare to the Fuchsian. You know what happens when gamma go to 0? This is the stuff you're saying? Or? What kind of projective structure this gives?
I think we will discuss afterwards. But not so sure. I think we will discuss. I already don't really know what is a good Teichmüller space to consider for when you have conical singularities. Yeah, I think there is this thing by mod 0. Yeah, we might be able to do something with those.
Any
I have a question, but for Sylvain. It's related to how do you get in physics the C gamma? What's the argument to get these coefficients?
I don't know. In fact, I'm not sure we get this C gamma. I think the jump in boundary conditions can be derived by different methods, by bootstrap method, by considering a few correlation functions. But I didn't see a calculation of this.
This is done in Belavin, but the way is wrong.
Thank you. But yeah, in Belavin, they already know this. There's at least some intuition on this classical function, and they do get this coefficient. The way they derive them, honestly, it's for me it's black magic. But it's really in a conformal bootstrap setting. You make some. Basically, you use the explicit expression of the structure constants.
The assumption is that there is only one primary field of a given conformal dimension.
Yeah.
So you write that it's proportional to this primary field, and then they do lots of computations with those formula or structure constants.
You really need the explicit expression of the structure constants for boundary Liouville. But here, actually, the way we derive, you derive them with Baojun, and I get them, it's completely independent of this. The expression of the structure constants. And actually, this machinery can be implemented in other settings.
So let us thank the speaker for a very nice talk. Let's off break.